Welcome to today's topic, which is improper integration. Okay, so I'll actually start by looking at a proper integral, I suppose, just like we've seen many times before. Okay, so you'll just have to trust us for now that if we integrate this function from 0 to 100, and you can do it a couple of different ways, you get that to be about 3.12. Okay, and we'll take the same integral, but instead of integrating from 0 to 100, let's integrate to 0 to 1,000. That's 3.13, nearly 3.14. Let's go to 10,000, it's 3.1414. And so what if we could integrate this to infinity? What does it appear that these values are heading towards? Okay, well, the eagle-eyed amongst you may have noticed it looks like this is going to be about pi. Right, we're already at 3.14, we're getting pretty close to that 3.14159. So it looks like these values are heading towards pi. Okay, but really what can we do here? What is this kind of integral? Well, this is improper integration. And what we're talking about here is, well, instead of taking the integral from 0 to infinity, let's integrate from 0 to b, and then take the limit as b goes to infinity. That's kind of what we've been doing in that previous page. And let's do exactly that. So we integrate this. The integral of 1 over 1 plus x squared is arctan of x. And so the 2 just multiplies it by 2. So we get 2 arctan x, and of course that's between the values, the constants of integration, b and 0. So we plug in the b, we plug in the 0, and we'll think about what each of these values are. I'll take the right hand one because that's easier, that's actually just 0. Tan of 0 is 0, so arctan of 0 is also 0. But let's think about what happens as b goes to infinity to arctan, and if we just take a quick diagram here of what arctan looks like. Remember, it's the graph of tangent but reflected in y equals x. And so it looks like this if we just take the one piece, and it appears that as b goes to infinity, arctan is going to pi over 2. It's about 1.57 there. So we multiply that by 2, we get that it's pi, so we have pi minus 0, and sure enough that's pi. And that's what it looked like our values were heading towards on the previous page. Okay, so this is an example of improper integration, and maybe we'll come up with the theorem. Okay, so we're going to let f be a continuous function, and it's going to go from a to infinity, at least in the top example. And we're going to do exactly this. Instead of integrating from a to infinity, we're going to integrate from a to b, and take the limit of that as b goes to infinity. Okay, that's our first type. Our second type, well, now instead of going from a to infinity, we're going from negative infinity to b. So again, we're just going to replace the negative infinity there with an a, and take the a approaching negative infinity. Okay, and then finally we could have it where it's in fact going from negative infinity to infinity, and essentially we do both pieces. We go from the a going to negative infinity and the b goes to infinity, and take both of those integrals. And then this is a very important piece here. We say that this converges if the limit exists, otherwise it diverges. Okay, so we're going to talk a lot about converging and diverging, and you'll see a lot more of this when we do sequences and series in a few weeks. But for right now, we're just interested in these integrals, and we say that if that limit exists, then they converge. If not, then it diverges. And in the third case, the case here where it goes from negative infinity to infinity, they both have to converge. Both limits have to exist for it to converge. Okay, so let's take an example. So we've already actually seen one example, but let's leap into a couple more. I'm going to take all our examples in pairs today, and we're going to take them to be very simple. Okay, so we're integrating 1 over x squared from 1 to infinity. Okay, so just as we suggested, instead of integrating from 1 to infinity, we're going to replace that infinity with a b and take the limit as b approaches infinity. And from this point, it's pretty straightforward. The integral is very standard. It's x to the negative 2, so we integrate, we get negative x to the negative 1. And our limits, our bounds are still 1 to a b. We plug in the b, we plug in the 1. And at this point, we can now take this limit. Now notice we have the b to the negative 1 as b approaches infinity, and that's just going to go to 0. So we get 0 plus 1, which is 1. And since that limit exists and is finite, we get that the integral is convergent, it converges. Okay, and we'll take another example. Looks very similar. Previously we had 1 over x squared, now we just have 1 over x. But we're going to do exactly the same thing, replace the infinity with a b and take the limit. We integrate, and this time our integral, remember the integral of 1 over x is just natural log of x between 1 and b. Plug the b and the 1 in again, but now this is different. Okay, in the previous case, as b went to infinity, our limit was 0. In this case, as b goes to infinity, natural log of b is still going to infinity. So this diverges. We can't get a finite value. So even though those two examples look very similar, in fact, we got two very different conclusions. The first one converged, the second one diverged. Okay, so let's change it up a bit. Let's look at a different type of integral. And I'm going to be bad. I'm going to be naughty and do this when I shouldn't. Okay, so we're going to integrate this from -2 to 1. Yeah, it's 1 over x squared. Let's integrate just as we've seen. Everything looks good. We add on to the power divided by the new power. Get negative x to the -1 between 1 and -2. Plug the values in, plug in the 1, and we get a -1 over 1. Plug in the 2, and it actually gets negative, so it's positive. So we get 1 over 2. So we get -1 plus a half, so that's minus a half. Okay. At this point, it appears I've done everything correct. However, already instinctively, this doesn't feel right. For a start, this function is 1 over x squared, so it's always positive. So how could we have got a negative area? Remember, this is the area under the curve. Well, let's look at a diagram of this. This is the function 1 over x squared. Okay. And if you remember back to Calc 1, one of our rules was we can only integrate within a region if the function is continuous within that region. And in fact, between -2 and 1, at the origin, at 0, this is not continuous. Okay, we have a discontinuity at 0. Therefore, we should never have been able to do this in the first place. This was just wrong. This was bad. But it raises the question, what do we do here? What do we do at 0 where we have this discontinuity? And that's going to be our other type of improper integration. So this time, instead of having the values going from sort of a to infinity or negative infinity to b, we're going to have an infinite range. Okay, so we'll assume somewhere within the range at c, when x equals c, we have some sort of vertical asymptote. In other words, it's going to infinity, or possibly negative infinity. And now to find this, we're actually going to break the integral into two pieces. And in each case, replace the c with a t, and take the limit as t approaches that c. Okay. So in this case, we're going to approach it from the left. In this case, we're going to approach it from the right. Then we add those two pieces together, and we get the integral. And again, we're going to be interested in, does it give us a finite number? Does the limit exist? In which case, we can call it convergent. Otherwise, it's divergent. Okay, and again, we're going to take a couple of examples. To make this a little simpler, I've just taken the vertical asymptote to at one end. So in this case, you'll notice we have a 0 right here as one of the limits, and our function is undefined at 0 because it has a vertical asymptote. So we're going to replace that 0 with an a, or a t was an example, either way, it doesn't really matter. And we're going to take a approaching 0, in this case from the right, because it's the lower limit, it's going to approach it from the right. And we're going to integrate from a to 1. Now again, once we've reached this point, the integral is just the same as we've done before. It's just the power rule next to the -1/2. We can plug the values in. We get 2 root 1 and minus 2 root a. And now as a approaches 0, that's okay. This piece approaches 0 as a approaches 0. So this is just 2 minus 0, which is 2. And again, we'll say that this converges. Okay, and we'll take another example. This looks very similar now. Our function is 1 over x squared instead of 1 over root x, but we still have the limits being 0 to 1. Okay, and again, we're going to replace the 0 with an a, and take the limit as a approaches 0 from the right. But again, we just integrate very simply. We use the power rule, just as we've seen many times. Plug in the limits, the 1 and the a. So we plug in the 1, we get -1. We plug in the a now. Okay, we get a to the -1, and we want the limit as a approaches 0 from the right of a to the -1. Well, in this case, that limit doesn't exist. Okay, that's some kind of infinite limit. So in this case, we say that this diverges. So once again, we've seen a case where it converges, a case where it diverges. And in fact, all 4 of our previous examples have hopefully led us to believe that this might be true. Okay, so we're looking at one particular type of integral. We're going 1 over x to the p. Okay, And in the first case, well, let's consider this 1 over x to the p, and we'll integrate it from 1 to infinity. This was the first case we saw. Well, if we do that, this converges as long as p is greater than 1, right? We saw the example where the p was 2, where it was x squared, and sure enough that converged. But it's going to diverge when p is less than or equal to 1. And in fact, we saw the case where p equals 1, and that diverged. So that's always going to be the case, that we integrate 1 over x to the p from 1 to infinity. It's going to converge when p is greater than 1 and diverge when p is less than 1. On the other hand, if we integrate from 0 to 1, so now the 0 is sort of the bad piece, the piece where we have the infinite range, the vertical asymptote. If we have 1 over x to the p now, it converges if p is less than 1. And that was the case where we saw where it was 1 over root x. In that case, p was just a half. Whereas it's going to diverge when p is greater than or equal to 1. And that was the case we saw when it was an x squared. Okay, so we'll keep those in mind because they're handy and useful. Again, we'll also see this when we get to sequences and series. You'll see why this might be useful. Okay, so we've got just one more thing to do. So sometimes it may be the case that finding our integral directly might be a little hard, but we can use a direct comparison for these improper integrals to help us find whether an integral is convergent or divergent. Okay, so we're going to assume that the f's and the g's are both positive, and we're always going to assume that this f of x is less than or equal to g of x. And if the f of x is less than or equal to g of x, then the g of x converges, then the f of x must also converge. Okay, less than something that converges must also converge. And again, we'll just make sure we assume that these are positive. On the other hand, if the f of x diverges, if the smaller one diverges, then the larger one, the g of x, must also diverge. In other words, larger than something that diverges also diverges. So we take a couple of very, very quick examples of that. Okay, we've just seen that 1 over x squared converges from 1 to infinity. And let's take 1 over x squared plus 5. Well, 1 over x squared plus 5 is less than 1 over x squared. Therefore, if 1 over x squared converges, then 1 over x squared plus 5 must also converge if we take that integral from 1 to infinity. Okay, it's less than something that converges, so it converges. And if we flip it, we know that this diverges. We know that 1 over x diverges. And 1 over x minus 5 is greater than 1 over x. And so greater than something that diverges must also diverge. Okay, so those are just a couple of very quick, simple examples. Obviously, we can look at more complicated, particularly more complicated functions. In these examples we've seen involving pretty simple functions. But that's all the theory we have for today.